Hello everyone. My name is Yosuke Tomita. I'm a physiotherapist and I'm an assistant professor in Takasaki University of Health and Welfare in Japan. Today, I would like to give you a short lecture on the application of robotics in clinical practice of rehabilitation. This lecture consists of two parts. And this video is the lecture 1, so here I will give you a general information of robot-assisted rehabilitation, including some situations surrounding robot-assisted rehabilitation in Japan. And the second part of the lecture will be more specific to patient cases, where I will introduce a specific example of application of an exoskeleton robot used in clinical settings. So first, I would like to introduce where I am now. Takasaki University of Health and Welfare is located in Gunma, Japan. Gunma is the right in the middle of Japan, as called berry button of Japan. And here is the Gunma. It is well located and you can access to Gunma by train from Tokyo in an hour. And we have so many hot springs and good mountains. So this is very famous hot spring called Kusatsu, and there are so many mountains. So if you have a chance to visit Japan, you're welcome, and please come and visit us too. I'm having this opportunity to give you a lecture as a part of a partnership between YAMC and Takasaki University of Health and Welfare, in short, UHW. We have a partnership agreement between universities, and every year we have an annual student exchange. In September, Japanese students visit Uvascula for about 1 week to 10 days, and in February, young students visit Takasaki in return. Every year, we have a few physiotherapy students from YAMC side too. And in 2018, we had a single-year project called Mentor Project, which involved a student exchange program specific to robotics and mentoring. A student from YAMC visited us for 2 months, where the students joined undergrad lectures in Japan and also conducted a survey on robotics in rehabilitation. As a continuum from Mentor, in this lecture, I would like to talk a bit about robotics in rehabilitation. So, why robotics in Japan? Well, in Japan, robotics have obtained interest for decades due to a few reasons. I'm gonna get into details for each point from now on. The first part is that because traditionally we tend to like technologies, robot requires the integration of both software and hardware engineering, and metal and wooden engineering have been developed very uniquely in Japan, as we can see in many traditional craftworks. And we also have a big gaming industry, as some of you may know. For example, Super Mario or some other very famous video games. And those big game industry also help to develop human resources who can capable of making those softwares using software engineering technologies. And for example, this small doll in the middle of the slide is designed about 250 years ago in Japan, where this small doll will deliver a cup of tea automatically. So once it walks and approaches to someone, and if someone picks up that cup of tea and bring it back onto the board, and then this guy will turn around and go back to the initial position. And I don't know if this robot is very efficient and very safe, But at least you can see we have been interested in robotics for so long and mainly motivated by a curiosity. Another reality is that our social structure is rapidly changing due to aging population. Maybe similar situation in Finland, but the rate of the change is so rapid in Japan. Here you can see age composition in the upper panel. So in 1950, it was just like triangle, and in 2005, now the structure has been so changed, and you can see the baby boomers are going older and older, and by 2055, the population composition will be totally different, and the majority of the population will be uh, older people. So we can see that the lack of human resource in many industries will happen in very near future. So due to the less and less working population, the robots are expected to or have been already working in many different industries to substitute some part of human labor force. And the last part is the cultural background. I have already covered some of them already in the previous slide, but we have many kinds of anime, manga, or video games about robotics. And exposures to robotics from early childhood may also have played a role to increase general interest in robotics. For example, in 1990s, we had a big boom of Aibo. It's the type of pet-like robot toy produced by Sony. Recently, its new version was released, and it's been another big boom of the robotic pets. I would like to shift the topic to the application of robotics in rehabilitation from now on. There are many classifications of robots. So here in this lecture, I would like to categorize the robots from the viewpoint at which body segments interacts with the robot. The first category is the end effector robotic devices, as shown in this slide. And in this type of device, the robot provides assistance or resistance only on the endpoint. So for example, in this example, the interaction of the person, this lady, with the robot is limited to the hand, which is the endpoint. So in the upper limb robot, it is usually the hand or forearm that is fixed with the robot, while the other part of the body remains free. So although most of the robots of this kind is used only for upper limb, there are a few types of end effector robotic devices for lower limb, as shown in the lower panel here. Advantage of this robot is that it is easy to wear. And also you can apply forces to many different directions, so the client can train different movements with this robot. And it does not require intensive monitoring or manual assist of the therapist, so end effector robotic devices, especially those for upper limb, can be very useful tool for self-training. One of the disadvantages of this type of robot is that as only end effector is fixed and constrained, the client can move other body parts freely how much ever they want, often resulting in compensation. So for example, when a client with a stroke is performing forward-reaching task with the affected arm, the client can reach the target with or without bending their trunk. So it is necessary to monitor or constrain compensation while they train with the end effector robotic devices. Another type of the robot is the exoskeleton. This type of robot consists of one or more sensors and actuators that detect the client's movement and produce appropriate assistance at right timing of the movement. It can be an assistance for one specific joint, like elbow for this one, and ankle joint for this one, and hip joint for this one. Or it can be for multiple joints as shown in those two devices. With those exoskeleton devices, you are not restricted to a certain space, so you can wear the robot and move around freely and perform the task that where you usually do those tasks. And another advantage is that you can change the level of assistance for specific joints separately to optimize the level of assistance. So for example, for this robot, they have actuators and sensors for the hip and the knee joints. So you can, for example, for the hip, you may want to assist for the extension, while you may want to assist to flexion. And you also can change the level of assistance differently. So you want more assistance on the extension of the hip, while you only want some small assistance on the knee flexion. And this would be very beneficial for the patients with spinal cord injury because they have weakness in specific movement while they have residual strength in other movements. But the big disadvantage of this type of device is that it takes time to wear. For example, hybrid assistive limb, so-called HAL, and it is this one. It takes about 10 to 15 minutes to wear it, and you need to attach electrodes on patient's body. So this is why it takes so long to wear. While this placement of the electrode is very crucial for this device to produce very natural movement as the patient intends. And another disadvantage of exoskeleton is that due to its flexibility of the setting, as I mentioned, it can be actually very complicated for the beginners. So we cannot underestimate this disadvantage because it can be a big psychological barrier for the regular use of robotic devices in clinical practice. Now, I would like to talk about the general benefit of robots in clinical practice. Here, I listed 4 benefits, and I will go one by one. And the first benefit is that using robot can motivate the client. In robot-assisted training, we can adjust the task difficulties by changing the level of assist. And this allows the client to perform the task at the optimal difficulty. And robot-assisted rehab allows us to create a game-like environment, which allows the client to perform the task without getting bored. And also the assistance of multiple joints especially, this allows the performance of difficult tasks that the patients usually cannot do. For example, even the patients with complete spinal cord injury, the patients can still walk with those devices, and it really leads to the motivations. You can find a lot of videos on YouTube where the patients wear those exoskeleton devices and walk, and you can see from their face and their family reactions of them. And those motivation really leads to continue their rehabilitation. And this is also the case for the patients with ALS, where their physical function will deteriorate, but they will need some rehabilitation to minimize those deterioration and complications. So the robot therapy will also give some motivation for those patients too. And for the motivation, some studies shows that when the robot-assisted rehabilitation is performed in group, it actually gives more motivations for the patients. So if you want to enhance the motivation of the patient, then it may be more beneficial if you perform those sessions with another patient. And the second point is that you can produce the same movement with the same assistance and with the same direction for the assistance for many times, which is very difficult to do so manually. As for the repetition part, studies have shown that less energy is consumed when the person performs the same task with robotic devices compared to when the patients or the subject doesn't wear the robotic devices. This makes a lot of sense because the robotic device provides some assistance on the movement, so the energy consumption is less during the repetition. This allows the patients to concentrate more on the motor tasks without feeling fatigue. And the second point is that you can change the task environment. For example, if you're doing upper limb and effector robot and you are performing the game-like environment, you can change the setting of the game of this or the scene of the game very easily. So you tend during the repetition, if the condition remains the same, you may get bored very easily. But the feature of changing the environment allows the patients to perform the tasks in repetitive manner without getting bored. And the biggest benefit for the repetition is that with the robotic devices, you can optimize the level of assistance depending on the level of the patient's movement performance. So the motor learning is mostly enhanced at the level of not too difficult, but not too easy. So by changing the level of assistance for appropriate level, then you can optimize and enhance the motor learning process. And the third point is that the movements are reproducible with those devices. Again, it is very difficult with the manual assistance. So it is another benefit. So for example, here in this slide on the upper panel, it's the walk-in of the patient with incomplete spinal cord injury during the walk-in. The upper panel shows before the session with exoskeleton, and the lower panel indicates the walk-in with exoskeleton device. And here on the upper panel of each video, it indicates the hip flexion angle. So here you can see without wearing the exoskeleton device, you can see those bumps, the levels, especially for the yellow part, are less consistent. See, you can see a lot of bumps, so it's very spiky. Whereas with robotic device, you can see those yellow dots are concentrated on line, indicating that the patient was able to extend their hip at the same angle throughout the gait cycles. This is because the exoskeleton allows the patients to reach, it continues to assist until the joint angle reaches to a specific joint angle. So this reproducibility is another benefit of the robot. And the last general benefit of robot is that as most of the robotic devices use sensors to optimize the level or the timing of the assistance, it actually measures those variables at the same time. So, for example, with the robotic device that I have just shown in the exoskeleton, it measures the joint angles and the foot pressure, which gives us the information of the position of center of pressure, and also some acceleration signals as well as the EMG signals, which gives us the information on the muscle activity. So you can get a lot of different variables and measure, and then you can give those measures as a feedback. So for example, with the force information under force applied on the foot, you can see the symmetry of the weight bearing. So you can give the feedback on that using the device too. So here in this slide, you can see bunch of the parameters. Like here, you can see the patient's COP position on right side and left side. And here it's written in Japanese, but it gives us the level of actual EMG level. So if it goes up, the patient is able to exhibit greater muscle activity. So you can also give some feedback on that too. So if this is the center of pressure of both sides. So if it is shifted to, for example, for the left hemiplegia patient, if it is shifted toward the better side, a less affected side, then you can point out that the weight is more bared on the less affected side. So please try to bear more weight on the more affected side, like that. So with those robotic devices, you can use those sensoring technology not just for producing better movement, but also for feedback for the patients on the performance of the movement. Until here, I have talked about the benefit of the robotic devices, but of course, nothing is perfect. So the robot also has a lot of downsides. The first limitation is its cost, resource, and its first cost and the time. As I mentioned, especially for the exoskeleton, it takes a lot of time to prepare and also to clean. And another disadvantage is the human factor. As I mentioned in the beginning of this presentation, there is a big hesitation on new technology in clinical settings, both for the client and therapist. And this may create dependence on the devices. So, for example, the client may not need robotic devices anymore because the patient is able to demonstrate the task without any assistance, whereas the patient may feel that the robotic device is still necessary because it's too awesome. So you may need some more additional efforts to convince the client that the robotic device is not necessary anymore. And there is also a technical downside. For example, as I said, especially for exoskeleton, the setting is somewhat complicated, and it's the downside of the flexibility. And the maintenance also costs some money, and also it may be broken. So you need constant maintenance so that it functions well. And just for information, in Japan, robot-assisted rehabilitation is covered by insurance only for HAL and only for 8 types of intractable diseases, like ALS and some muscular atrophy and other types of diseases. So, for example, stroke is still not covered. So, if you want to undergo robot-assisted rehab after having stroke, you need to pay extra money, or the hospital has to pay extra money to provide uh, those types of rehabilitation. But there is a huge need for this, and there are ongoing clinical trials to prove the effectiveness of the robot-assisted devices, and it's been already phase 3 trial. So after it's been completed, it seems like the result is positive. So in the near future, there will be more types of diseases that will be covered by insurance, and probably for other types of devices too. So can robots be a magic bullet? Well, it's still questionable. We don't know the answer at this stage, but it is very unlikely to be so at this stage. I have to say that. It is very important to note that there are several negative or neutral evidence on the effectiveness of robot-assisted rehab. This is an example reported by Vani et al. In 2012, where they reviewed randomized controlled trials of robot-assisted rehab programs in patients with multiple sclerosis. Here we can see that overall gait speed and walk distance did not differ between robot-assisted gait training and controls. So here, if this diamond's shape is shifted to right side, it means that it favors robotic assisted gait training. But all of those crosses, both for timed walk and walk distance, both for temporal and spatial parameters, this diamond crosses 0, meaning that it doesn't favor any either of those control or robot assisted training. So there's no difference on that. And for example, this is a recent study that compared the effectiveness of 3 patient groups of stroke in the robot assisted training group. The patients underwent only the robot assisted training with the in-effector robot, as I showed in this slide. In the second group, the enhanced upper training group, the patients underwent task-oriented training without using any robotic devices. And in the control group, the client underwent the usual care, and all groups underwent trainings of 45 minutes for 3 times per week for 3 months. And the results are shown here in ARAT, which is the Action Research Arm Test. It's a clinical score of upper limb function, and Fugger-Meyer score here. And the bar graphs on the left panels indicates the scores of ARAT here in the ARAT, and here the Fugger-Meyer scores. At the baseline, here is the baseline at 3 months and 6 months. You can see all outcomes are improving in all three groups. And when we compare the effectiveness between groups, then the robot therapy had more favorable outcomes than usual care in Fugl-Meyer. So here you can see the line is not crossing zero. So it means that it favors the robotic rehab when it is compared with the control. But when the robotic device assisted rehab is compared with enhanced training, upper limb training group, where the patients underwent task-oriented training, then there's no difference between robot-assisted rehab. So it means that robotic device is better than usual care, but it's not more beneficial compared to task-oriented intensive rehab program. So, is this bad news? No, I don't think so. It is because it shows that the robotic device was as effective as enhanced upper limb training, which was very intensive for both in terms of labor. I mean, the therapist has to always watch and perform those tasks with the patients. And robot assisted training may be good for self-training. So in this study, they use the end effector robot for the upper limb, and it can be performed by the patients alone. And it's still as effective as the upper limb robot, upper limb enhanced training. And it can be used for remote therapy where therapists are not necessarily accessible. Like if the patient is living in very far away, then it may be very beneficial for those patients. And the results also indicate that the combination of robotic devices with enhanced upper limb training may maximize the motor recovery after stroke. And we can see there's a huge gap between the reality and the theory. It's because of the barriers, as we mentioned. So now I would like to introduce what I'm doing here in Japan, where now I'm trying to improve the access to robot-assisted training in clinical practice. And the aim of this project is to create a research environment where we can examine the effectiveness of robot-assisted training in clinical settings. And the study group includes 4 hospitals using HAL in Gunma Prefecture. And at this moment, we're still at the stage where we organize a focus group meeting where clinicians get together and discuss which standardized measure we should use. But this is a good start, and I hope we can use standardized way to measure the effectiveness of robot-assisted training, and somehow we can compare the effectiveness of the robot-assisted training with other types of treatment. And there is no standardized decision-making process for the application of robotic rehab. That's still immature industry or the field, and it needs to be further explored. But here, based on our experience, those 3 points are very important while you make decision for intervention with robotic devices. The first point is that you need to monitor motor performance or the other types of outcomes of interest. So you always have a specific goal that you want to achieve with the robot-assisted rehab, and it has to be measurable. And after each session, if it's possible, it's better to measure the effectiveness of the session for that for the outcome of your interest. If you don't see a lot of changes in those outcomes, then you may want to change the setting of the robotic devices or change the type of the robotic devices maybe, or the number of repetitions or the intervention time and so on. And for the second point, it's very important to consider the task specificity. As we saw in the research evidence, a lot of robotic rehab is beneficial to improve motor impairment in the ICF domains, whereas very limited evidence exists that robotic rehab is beneficial for the improvement of activity or participation level in the ICF. So it means that the improvement of the motor impairments due to the robotic rehab is not automatically transferred to other domains of ICFs like activities or participation. So in that case, it would be more beneficial to combine robotic rehab and task-oriented training. And it's also important that you measure appropriate tasks that's very consistent with the goal that you have. So if you're interested in improving the gait speed for like 500 meters, then the walking speed in T-meter walk test may not be representable for your goal. So like that, it's very important to consider task specificity for both training purpose and assessment purpose. And the last point is that if you don't see a lot of changes in the outcome with the robotic devices, you may want to consider whether or not you will stop using the robotic devices, or you should change the settings and so on. But before you do so, you'd better discuss with the client. It is because some of the clients want to use the device as a means for the recovery, but some patients, especially for patients with degenerative disorders like ALS, the robot-assisted rehab is not really for improving their gait ability, but it's more for maintaining their bone minerals level or to maintain their motivation and so on. So even if you don't see a lot of changes in motor outcomes, you don't quit the session with robot-assisted devices automatically without thinking. But instead, you may want to discuss with the client whether the client wants to stop using the devices or they still want to use it. So this is the last slide for this lecture. And take-home message of this lecture is that firstly, robot-assisted rehab provides motivation, repetition, reproducibility, and measurable environment. And secondly, there is a strong need to design a standardized decision-making process that allows clinicians to choose appropriate indication, settings, and assessment for specific robot. And lastly, there's a lot of potential for application of robotics in rehabilitation. And it's still a developing field. So you're more than welcome to be involved in the research and create evidence to enhance the robotic devices. And that's it for this part of the lecture. And thank you very much.